Morning, everyone. Today's going to be the last lecture here. As most of you know, you'll probably be watching this remotely. So just as a follow-up from the first 5 lectures, we went through a few lectures. We did a lecture on Da Vinci's work with the anatomical drawings and the human body. But one of the things that separated Da Vinci from other people of the time was his meticulous hand sketches. He used them both for artistic work as well as his military engineering drawing and as well as for construction purposes. One of the things we tried to touch upon in these lectures was how Da Vinci used simple geometrical structures for very complicated mathematical ideology. So whether he was modifying Archimedes' screw theory or using 6 simple machines for pulley systems and gears to gain a mechanical advantage at the time, he tried to tie things in with elements of nature. So he looked at wind, water in his designs. Similar to convection currents, we talked about with the motion of the heartbeat in the body as he looked at cadavers, it actually has a similar fluid flow background as convection currents in welding or other technologies. So to tie in with the military engineering, we did discuss his simple designs for tanks where there would actually be people in here and they could move the tanks on foot, as well as cannons and steam cannons. These are in the previous lectures. Today's lecture is going to more be geared towards his artistic work, but to tie in his artistic work as well as with some new technologies that's going on today. So as I said, his hand sketches were very critical, and as they looked at these codices that they found hundreds and hundreds of years later, one of the things that's important is the materials he actually used to draw this artwork on. There's a 5-minute YouTube video we're going to look at in a few minutes, but one of the things that's important to note is when they allow people to actually view these things, whether they're in a museum or not, one of the videos I saw said they wouldn't even allow the video cameras to shine the light on the paper material. So you have to figure it's 500-year-old paper, the preservation, historic aspect of it at this point. So in terms of art and music, so Da Vinci, most people think of him just as an artist. We've already discussed his military as well as design abilities in previous lectures, but some of the things to note here is most of the artwork, the size of the scale of these artworks. So this on the left is called Portrait of a Musician. The one on the right is Virgin and Child with Saint Anne and John the Baptist. So last lecture we showed some images of the Mona Lisa at the Louvre, and it's actually quite a small painting with respect to the frescoes and the other artistic work at the time. One of the things I wanted to point out in this document is the comparison of Da Vinci's work with, say, from another area of the globe. So this is actually tiger screen paintings from a museum in Japan. And what I want to show in this video that we're going to look at is actually going to be the materials that Da Vinci would have had to have used at the time. So it really is as simple as quill and pen. So before we go further, I think we'll go to the video here. It's a 5-minute video. One of the things we noticed with Da Vinci's sketchbooks was that Da Vinci actually erased and did multiple copies of the sketches. So as you saw right there, that's how you're able to basically erase in the 1450s to 1500s. So this technique would have been used for the sketchbooks. As you see here, some of the drawings that were visible in the sketchbooks. With respect to the artwork, whether it was oil on canvas or something else, one of the things to note on the previous slide was the size of the artwork. So for the Virgin and Child with St. Anne and John the Baptist, that dimensions of that were 56 inches by 41 inches. That would have been 142 centimeters by 105 centimeters. That is actually quite larger than the Mona Lisa in terms of size. So here you actually see how they would have used quills and ink at the time. You could just leave it on that till I'm done. I'm basically just talking over with some other comments.
What it could allow the artists to do is to draw very fine.
So as you see here, it was the ability to use the gum and the Arabic there to actually mix it in with a Porter Messel to get the inks that he could get this fine detail as you're seeing here on these drawings. So that's one of the things people take for granted when they look at something from 1450s is the level of detail in the artwork versus basically all he was using was a quill and a pen and then some other raw materials that allowed this compared to today where everything is digital. This would be in terms of non-destructive testing. When you look at these, this would be an application for 3D laser printing to get point scans of all the artwork, and then you could put that into a computer program and render it. So what you see oftentimes is that's what they do. They'll get what's called point cloud data, whether you're using coordinate measuring machines or other types of manufacturing equipment. You can also use this for artwork. And they have done it in the North End at Paul Revere's house. They did a full 3D laser scan of the entire historical house. So the same type of, it's relevant also for this historical work. So 3D laser scanning, laser printing, it also has applications for historical preservation.
Understanding how these words are produced in this process,
So that was from the Royal Collection Trust, and I actually thought it was a good representation of what the materials were at the time. So to tie that back in, as I said, this was about 56 inches by 41 inches in size scale, which is quite larger than the Mona Lisa if you look at them next to each other. Not only with artwork, but Da Vinci also had interest with respect to music. One of the things in terms of acoustics, we had talked about Da Vinci's interest in using science and technology. The same type of way he looked at wind and water for devices, he also looked at acoustics and optics. As you see here, there's a musical drum, a mechanical drum. So in the probably around 1460, 1470 time frame, this was designed, and it would essentially be if you were bringing your cavalry or the certain group of Italians were going to fight another group of Italians or French, this would be similar to somebody playing the fife in the American Revolution, a mechanical drum that moves with the soldiers as they're going into battle. Other devices that were also thought about by Da Vinci, some things as simple as a projector. So before there was even the ability to take camera, whether it was digital or film camera, Da Vinci was using his knowledge of light and reflection on how to make basically projection as well as reflection of images with mirrors. He designed this mirror room where you get a 360-degree view on how the mirrors come together. So he was not just a military engineer. He also had many other interests, music and machine interests. In terms of architecture, we showed some of the architecture last week of the time, some of these fortified castles. Da Vinci also looked into essentially what would be known as today the field of urban planning or architecture. And he did sketches on what he would have considered the perfect city. So here at MIT, they have an entire urban planning department. It's essentially how he would put things in proximity to one another so people can get what they need without having to go very far. And if you look at dorms in various universities, this is a whole new science and engineering with respect to students want to have things close to them in the dorm. So there'll be a food market, there'll be shopping, there'll be laundry. These things for the 1450s, Leonardo thought about, wasn't where to put the Wi-Fi router, but there was still quite a bit of thought in terms of what to put in proximity for the perfect city. Some additional artwork that is less known, but that I did want to highlight upon. So this is another piece of artwork which is at the Louvre in Paris, and it's known as Virgins of the Rocks. Its actual size is 74.6 inches by 47.25 inches. So that's about 190 centimeters by 120 centimeters. So these are almost fresco-like. We're talk about other maestros of the Renaissance time, in particular Michelangelo. But you also see these types of large frescoes, El Greco, if you go to Madrid, the Prado. You see that this was a type of artistic style where you have these frescoes that come up and have an arch-like feature to them. Two additional pieces of artwork are the Madonna of the Carnation, as well as the St. John the Baptist. So Da Vinci did both of these. If you looked at the video previously, there's simple as oil on canvas for the materials of the time. But the thing that was interesting is how he actually did the sketches on the canvas with the mortar and pestle and those raw materials. One of the things that people mention oftentimes, especially with respect to Mona Lisa, is Da Vinci's use of perspective and geometry in his artwork. We talked about this a bit with the Golden Ratio and the Vitruvian Man, but a thing that's important to note is with his eyes. Da Vinci took great caution and care when looking at where to place the eyes in his artwork. So people will often say, depending on where you look at the Mona Lisa, it seems like the eyes are following you. That is not an accident. That is actually a combination of his artistic ability with the geometrical knowledge that Da Vinci put into his artwork. What you're seeing here is from a various point source, you have rays. They could be rays of light, they could be rays of anything, but this would be where your perspective starts. And based on the various angles, Da Vinci took into account in his artwork where the eyes would appear to be focusing on from different angle perspectives, which is quite interesting and not for the time. This is, you have to realize, 1450s, there's still issues with planetary motion and Copernicus and things of that sort. So if you do look at the Mona Lisa, they often do say depending on where you are in the room, it doesn't really matter. It feels like the eyes are looking at you. And that was purposely a point of Da Vinci tying in both his artistic ability and his mathematical scientific knowledge. So in addition, the drafts here. So The Last Supper, probably one of his most famous pieces of art. One of the things that I found very amazing about this piece of artwork is just the level of detail in the draft. So if we compare this with the final product, you can actually see that in the final product, it almost looks simpler than the drafts. In the draft work, the level of detail is much finer with the quill and the pen. When he starts painting over it, it actually seems to lose a bit of the detail. One of the other videos I wanted to play is with respect to what we talked about a couple weeks ago in the anatomical drawings. We talked about the vortices and how he saw wind. And in some of his drawings where he took into account wind and water, he actually drew, before he could scientifically prove it, convection currents. So what you're going to see here is actually with respect to his thoughts on the human heart and what we're at in the 21st century with the ability to do computed tomography and 3D scanning. And it ended up showing that his beliefs on how the heart pumped were actually correct. So it took 450 years for the experiment to actually have the capability to be built, where they're looking at the vortices within the bloodstream. What you're seeing here is essentially similar to like a Bernoulli's theorem, where you're talking about turbulent flow. What you're seeing with the 3D model, it's the turbulent flow of a particular region within the heart. And that, as compared to Da Vinci's drawings, it actually shows that his beliefs in the 1450s, 400 years later, the technology was finally there that they could confirm the belief of the vortices. So that was found to be pretty interesting, and that's how you can tie in these things from hundreds of years ago to modern day technology. So to tie that in with the other artists of the time. So what you're seeing on the left here is the Sistine Chapel. This is actually within the Sistine Chapel, and this was done by Michelangelo. Some of the history was Michelangelo was essentially this up-and-coming young gun when Da Vinci was towards his later years in life. So Michelangelo, I believe, was around 28, 29 when he got commissioned to do Sistine Chapel. I believe it was something that Leonardo did inquire about but didn't get. So there was a bit of snobbery between these two great artists of the time. One of the things I wanted to show here with respect to the artwork is look at the varied levels of not just the tapestries, but the size of these different pieces of artwork. And this is just the roof, as I had mentioned last week. If you look on the sides, there's also artwork with respect to various regions of Italy. So this is the entire, this is couple hundred feet length floor here that you walk down, if not more. And it's covered with artwork. So just the scale in terms of number of artwork and sculptures and other pieces of highly valued historical art that came out of the Renaissance period was quite impressive. To tie in with not just the artwork of Da Vinci, but the artwork of others at the time as well. So I wanted to tie in with the thought of Da Vinci not just as an artist, but as a scientist and an engineer as well. And I wanted to kind of bring it into the 21st century on some of the things that we face both at MIT and other institutes with respect to where knowledge is going. So, many people have stated that the future is artificial intelligence. So with respect to artificial intelligence, we looked at from World War I, Enigma machines and other signal intelligence devices that were used 100 years ago. In the span of 100 years, now we are at the point where we're on the threshold of technologies that pass the Turing test. So Alan Turing was the individual who basically, for Britain, developed the way to reverse engineer the Enigma machine of the Germans in the war. This was how they were able to basically pull off the signals and reverse the cryptology on what the Germans were doing, where they were moving their infantry or panzer divisions. And there was strategic value for the war. It essentially, people will say without Alan Turing, we may be speaking German, all right? So there was very significant strategic value to being able to reverse engineer things 100 years ago. Now we're talking about reverse engineering things such as the human body. So we're tying in the knowledge that we have from brain scans and the non-destructive technology in with the computing power and the ability to intertwine it all together. So it's not just science, there's art. One of the things that Professor Eager says about welding oftentimes is welding is as much art as science. This is something, if you've ever welded before, if you had never had a acetylene torch in your hand, you can't just pick it up and lay a bead down your first time. It takes practice. One of the things that it's not in the engineering books is you have to have a feel for the torch as you lay a welding bead down, or the angle that you're going to weld in is critical to having a feel of doing it. It's the same type of thing with artificial intelligence. How can computers mimic that ability of humans, that sixth sense where they have a feeling of something's going to happen? And they're getting close to it with their ability to scan human brains and see which portions of the human brain light up under a functional MRI or some other tests. And this ties in with phrenology and these techniques that were considered in the 1800s and 1900s. A quote that I heard that I think is relevant is that personal privacy is the oil of the 21st century. So with all of these abilities to use computing power, you have to look at what they're actually looking at when they're data mining your clicks on social media or something else. We saw the outrage with the Cambridge Analytica scandal, but essentially people need to realize every time you're doing something digital, you should believe that there's going to be a backup copy of it somewhere. What's the implications for that militarily? So you can get election hacking, you can get hyper-targeting, not only of districts, but you can hyper-target election material to a unique individual's IP address. It's not that far from brainwashing. If you send somebody the same advertisements over and over and over again, there's been studies and Supreme Court cases on this where it actually has been proven that it's illegal to do. One of the famous court cases in the 1960s, 70s was Joe Camel cigarettes. And it was a Supreme Court case where they essentially said it was illegal because it was targeting for the youth. It made cigarette smoking appear to be cool to the youth of America, and it did not tell them all of the hazards associated with it. We're getting into the same realm with the ability to do things with computers, either hacking or artificial intelligence-wise. So one of the case studies or things I wanted to talk about today was Google. In 2016, they had what's known as this DeepMind Challenge, and it's the game Go. It's actually the Asian board game. And they designed a program where they used artificial intelligence, neural networks, and deep learning. And they called it AlphaGo. And in 2016, it actually went up against one of the world champions. So that 9-Dan Pro in the game of Go, that is like the highest level you can achieve. It would be like being the highest black belt if you were doing Taekwondo or something like that. In 2016, the computing power was able to beat a human at this game. And what's important about this is in the game Go, we talked about factorial and design of experiments. The number of permutations in the game Go, it's stated that there's more permutations in the game than there are atoms in the universe. So this is when you start thinking about how many different moves that a computer would need to know. It's quite impressive, the computing power. So how did they do it? What they actually did was they didn't go in and program it with every possibility. It would have taken way too long to program every permutation. When we talked about the design of experiments last week, that would be a factorial experiment based on every single square on that game. And the length of that board, that's how many factorials. And it changes as a conditional probability of the prior moves. So when you start thinking of that, the number of different possibilities becomes almost endless. What they did was they programmed the deep learning program with 30 million moves. They gave it 30 million moves that were some of the typical moves in the game. And then they let the program play against itself for a while to teach itself. So this is where the technology is actually going. To tie that in with the artwork, we talk about CRISPR. There's Steve Lyons talks about it from a intellectual property patent law perspective, but we are actually at the ability in 2020 where we can hack the human body, okay? So you can target specific portions of your DNA using CRISPR technology to either shut on or off either recessive or other types of traits. When I went to school, we started having this discussion with respect to nanomaterials on the ethics, and we touched on it a bit a couple weeks ago, but this issue of could you now make designer babies and things like that. One of the things that's important to note is it's not just an engineering question. It then becomes a moral, for some people, religious question as well. But at its basis, from a scientific viewpoint only, the technology is there to do these things. So the people who are doing the research along these lines need to realize that it can be used not only for the good things that they're touting, it can be used as a military or strategic weapon against as basically a 180 degrees from what it's marketed as. These are things that are important to know from not just the research side, but from also practicality side. I'll just point this out. This was an event I was at a couple weeks ago. This is called Artificial Intelligence in Healthcare. So we start talking about things that become ubiquitous. And when something becomes ubiquitous, then it has the ability to be exploited. So if you think of people as they get older in life, they all have their medications or things like that. We started talking about catering, putting nanomaterials into hacking into the world's pharmaceutical industry, things like that. Now they've taken it another step. They can even hack into the individual's bodies. And there's a lot of research out there on ingestible electronics and other things to target the electronics to a certain part of the body. They oftentimes neglect to point out that this could be used for biological warfare. So, as I had said, we're not just talking about military weapons in terms of aircraft carriers or nuclear submarines. Now, the human body have to be added into the threat matrix that needs to be taken into account for all types of warfare that, as a nation state, you have to be prepared against. Tie that in. So this is I put the title as a modern day Rorschach test, but the question is posed, what do you see when you look at that? It's not a singular image, but an individual does kind of jump out in the foreground. This is actually where the artificial intelligence and deep learning is going. And what this program was, it's known as the Deep Dream Generator. So it is basically the modern day combination of art, classical science in the terms that we've used with Da Vinci, computer science when we talk about the computing capability, and it was initially developed to assist scientists and engineers to see what a deep neural network is looking at any given time. So what it is, there's more than one image in play. So what happens is when a computer laser program or something related that has to have an optical reader on it, it sees more than just the Mona Lisa. What it sees is actually there's other pieces of art within the art. And this algorithm was designed as a way to basically do many simulations, whether you want to consider them like Monte Carlo simulations or not. But what is the neural network doing as it's looking at multiple images simultaneously? It ultimately, now it makes pretty cool psychedelic images, and it has become somewhat of a psychedelic art. But it's important to understand the algorithms, and this has implications towards biomedical and SpaceX for programming Falcon 9 and these other devices to self-land. This is the technology that's tied into it. So at its most simplest, to tie things in, Da Vinci was a curious person, and his sketches, he used his sketches basically as a way to develop his own scientific method. All right, to take it back to your high school or middle school physics, at its simplest, the scientific method says ask a question, you do your background research, you construct the hypothesis, and then you test the hypothesis. And when you start testing these hypotheses, that is where you either have feedback loops, or that is where in your programming, it branches off and pivots to a yes or no answer. And based on that, you use decision analysis to decide which route you're going to go. This is used for non-destructive evaluation, what it would be known as probability of detection models. So for structural components, for aerospace, for nuclear, for bridges, where you need to predict how long you can keep that bridge in service until the next inspection, they use these POD models to determine inspection intervals for 100% critical infrastructure. One of the things is based on that flaw size. Based on that flaw size and the fracture mechanics, based on the fracture mechanics and that flaw size, that is one of the inputs into what would be your algorithm that you're developing. So whether we're looking at it from an artistic perspective or infrastructure or military perspective, it's not that different. You can transfer the knowledge. You have a few known inputs. These would be what would be the critical variables for a sensitivity analysis. What are the inputs into the program? Based on fracture mechanics, it's that initial flaw size. And it's also how that flaw size is oriented with respect to the inspection technique. So if you have a flaw size that's 90, that is not a surface cracking flaw, but a near surface, you can use a lot of techniques. And if you're just going perpendicular to that surface, you'll miss it because of, for an ultrasonic type, if you're thinking of longitudinal scan, it just a pulse echo back and forth. You can miss flaws if they're oriented a certain way. Even though you can detect that size, that flaw size, you can still miss it in the detection process because of how it's oriented in the structure. The loading conditions, to tie it all in, you have your crack growth equation here. But if you look at we look at the POD model, we look at the fracture model, there are some things that vary from inspection to inspection. All right, you have material properties, which is different based on the application. If we're looking for aerospace for blades and discs, there are very unique material properties for turbine blades. Compared to the example we gave for the running rail, where fracture toughness for a running rail is actually quite low. The fracture toughness is less than 4 foot-pounds per square inch typically for commercial running rail. That is extremely low fracture toughness for something that is, the entire network is essentially made of rolled carbon steel. That's quite a low fracture toughness, and when you see rail fractures, one of the things you often say is, why hasn't AASHTO or other agencies put a minimum requirement in for fracture toughness? The simple answer is costs. It will cost the steel companies more to actually comply with a minimum fracture toughness of 25 foot-pounds or something like that. Right now, when you do Sharpie tests, you see 3 and 4 foot-pounds as the value. So the material properties change from it. That's what makes it a case-by-case basis. So even though you can look at one rail fracture and know it's fatigue, you can't assume that all the rail fractures will be fatigue. This is the difference between you having things to look for and then actually doing the experiment and tying it into your scientific method. One of the things I wanted to bring up with respect to the Google Deep Dream and these algorithms is what's known as Bayes' theorem. And that's B-A-Y-E-S. So Bayes' theorem is based on conditional and posterior probabilities. And one of the ways that, for the layperson, it's easy to think of is forecasting the weather. So when you see a weather person say it's going to be a 70% chance of weather, when you look at the weather nowadays, oftentimes they'll put every single thing in the, if you put snow, rain, fog, and put everything in there, then you could say you're right? But that's not what people want. What people want is they want it to be specific and narrowed down. So one of the ways to do that is Bayes' theorem. And it's what it is, it's a formula used to calculate posterior probabilities based on prior knowledge and your prior research and experimentation. So this P of E is your prior probability. So it rained the last 3 days. That is your knowledge you have. Will it rain tomorrow? Will it rain the next 3 days? And this is one of the important things when you're doing research, whether it's undergraduate or graduate research. How do you pose the question? What's the question you want to solve from your research perspective? And this is one of the ways when you're doing experiments to kind of guide you in terms of how you evaluate the data from the experiments. So PE is your prior probability of this event E occurring. You also have this PO divided by E. That's a conditional probability that's tying in your mixed mode effects. All right. So observation O happening during event E. And that's what differs when you look at your various POD models, fracture mechanics models. Your conditional probability depends on which application, which industry. Are we talking aerospace? Are we talking transportation? And that's where your materials properties play a very big role in changing these values. So ultimately, you have posterior probability. So after something's happened, post, right? After something's happened, you have knowledge of it. As you gain knowledge, you can then put things into statistical models. So this is your posterior probability, this whole term, that an event happened based on an observation. It's based on a conditional probability. So this whole term here is a conditional probability. If this happens, if I ride my bike, there will be an 80% chance of rain. So yeah, they can be, as you know, these conditional probabilities, how you phrase the question, it doesn't need to really make sense, but you can phrase the question any way you want. If this is a zero, the whole thing drops to zero. So one of the other things to note with the probability is that you have to have the probability of an event happening versus E hat, the event doesn't happen. So if it's a go, no go question, it has to either go or it has to not go, and the probability total has to be 1. So that ties back in, and if this is 0, this whole thing drops to 0. It's as soon as you put a conditional probability that even has the slightest chance of happening, that is when the other events become more important. But you have to take into account that the total has to be 1. And with the algorithms and the other technologies they're using today, essentially they're tying in Bayes' theorem, and you have a priori knowledge, things that you know beforehand, and then you have experiential knowledge as you're doing more experiments. So it's tying those two things in hand, and it's the same as whether you're looking at things for the human body and brain biological or material science infrastructure related problems. It's all how you're going to phrase a couple statistical questions, and it's all to what detail you're going to put these things in. So we talk about 6 sigma in manufacturing. That's from a Gaussian distribution. 6 sigma, if you go 3 sigma, that's 99.7%. Then you go further, that ties in with Professor Eager's total quality management module. But when we start talking about putting satellites in space and 100% critical structures, that humans can't easily go out in space and repair these things. You need to have these values start getting really low in terms of probabilities. All right, so for NDE methods for various flaw types, this is a bit of an older table here, but it's not necessarily the classifications. You can argue on the classifications on whether techniques can be used on surface or not. In some cases, even though it's possible, it's just not used because the sensitivity is not there. This is where we tie in reliability versus sensitivity. But you have many methods to choose when you're thinking about long-term maintenance of critical infrastructure. Whether it's a volumetric flaw you're looking for or a surface crack, that would be a planar flaw. The type of flaw, you have to have a knowledge on the type of flaw you're looking to inspect for. If you don't even know what type of flaw you're looking to inspect for, then your chances of finding that flaw would be much higher. So an understanding on what flaws are being looked for are critical. So there's an analogy towards the space race, the nuclear race. Now we're in the artificial intelligence race. The last thing I wanted to tie in here, the last couple slides, was, from 1482, this was essentially Da Vinci's job application to the Duke Ludovico Sforza, who commissioned a lot of his artwork and a lot of his war machines for the time. Some of the things I found interesting was basically Da Vinci claims that he could build any war machine that is needed. But He talks about he can make types of cannons, portable or not, to hurl stones like a hailstorm. So it's how you sell it, right? It's if this was a public relations or a marketing class, we'd say you sell the sizzle, not the steak, right? It's actually how Da Vinci convinced the Duke Ludovico Sforza to give him money so he could go then do artwork and the things he interested. And yeah, he talks in some absolute terms here. He talks about all the different things that he can build, and they're easily portable. The things that I put it in as resume of a genius, because it's not just the claims. If we're talking about a patent, a patent has claims. It's the end statements here. Basically, he's more than readily disposed to demonstrate his abilities to design. So in modern day warfare, we talk about mutually assured destruction when there's such technologies available that it could be the end of civilization. This last statement here is almost as important as all the other claims. The fact that, well, if you don't believe I can do it, I can show you I can do it. So this was essentially how Da Vinci got hired for his first commissions with the Duke Ludovico Sforza. It works for some people in the 21st century, but you have to have the technology and the knowledge to back it up. So I hope I tied Da Vinci's ideologies and some of his technical knowledge from the 1450s, 1500s into what can be relevant for today, both from material science and infrastructure, as well as more biological, artificial intelligence perspectives. Thank you very much.